Hello again. Today we're going to be starting a unit on simplifying, proving, and solving trig expressions and equations. To begin, I'd like to talk about what an identity is. An identity is an equation that is always true. And we're going to be working with a lot of identities in this unit. What's it used for? A couple of things. First off, get rid of that underlined and bold. First off, we are going to be given some pretty complicated trig equations. We're going to be taking identities, which are often smaller true trig equations, and we'll be using those to prove that the bigger, more complicated ones are in fact true. Second, we'll also use identities when we're solving equations later on in this unit. We'll be solving in the last lesson or two. In the meantime, we'll be using these tools to simplify expressions and to solve equations. Now, to begin some of these tools, these first 6 tools are the reciprocal identities, and we've touched on these earlier on in our study of trig. So first off, we have sine of theta. Now remember that sine of theta and cosecant of theta are basically the same thing, except for they are reciprocals of each other. Remember that sine was y over r and cosecant was r over y. And so we can say they're reciprocals, and therefore we can write them as reciprocals of the other. Now same thing with cosine and secant. Cosine of theta is 1 over the secant of that angle, and the secant of that angle is 1 over the cosine of that angle. That's an interesting one. Tangent's 1 over cotangent, and cotangent is 1 over tangent. Next up, the quotient identities. Quotient means a division expression. And so these are going to be division expressions. Tangent of theta is the sine of that angle divided by the cosine. We'll be using these quotient identities quite a bit. And the cotangent of an angle is the same as the cosine over sine. Now this makes sense because earlier we saw that cotangent and tangent are reciprocals. So it makes sense that the cotangent's quotient is the reciprocal form of the tangent's quotient over there. Alright, next, the negative angle identities. For this first one, it is helpful to remember that the sine graph looks something like this. And on the other side, it's sort of reflected but flipped upside down. So essentially, we can look at any point on our graph. Let's say this positive angle. I'll call this positive angle alpha. If we went to negative alpha, same distance but to the left, we would see that the y value is the same distance vertically up and down, but it's negative instead of positive. So if this were like 0.8 units right up here, this negative angle would be negative 0.8 units there. And that's true for any angle for sine. So what we can say here is that the sine of the opposite of an angle, let me erase this now so we've got room to write. The sine of the opposite of an angle is equal to the opposite of the sine of the angle itself. Next up with cosine. Cosine graph looks, remember, like this. It goes on from there, and then it does that, and it goes on from there. What I'd like to show you is that if we took an angle here, found its y value, let's say that was 0.9, and then we did a negative version of that angle, the y value would be the same as the positive version of that angle. And that's true for any cosine there. So we can say that the cosine of the negative of an angle is the same as the cosine of the positive version of that angle. And we don't use these negative angle identities maybe quite so much as the quotient or the reciprocal identities, but they're powerful in certain contexts. Next up, the Pythagorean identities. We've already studied earlier the most famous Pythagorean identity, which is that sine squared of an angle plus its cosine squared equals 1. Now, I'd like to point out that if we do a little moving around of these terms, we can come up with a couple other identities which look different, but they're basically the same thing. They're just more useful in certain contexts. So if we took this sine squared of the angle and then subtracted it from both sides, we'd end up with just cosine squared on the left side. And then we would have 1 minus, okay, that's a bit obnoxious. We'd have 1 minus the sine squared on the other side. Now, if we left the sine squared here, we started over again. Let's say that we left the sine squared here. Subtract cosine squared from both sides. This is what we end up with. Alright, next up, the other two Pythagorean identities. So these two are different, but they're basically the same thing, just subtracting. Another two come if we were to divide both sides by cosine squared. So if we divide the left side by cosine squared, sine squared divided by cosine squared would become tangent squared. And that's because sine over cosine up here is tangent. Cosine squared divided by cosine squared is 1, because something divided by itself is 1. And then 1 divided by cosine squared is going to be secant squared, because of that identity. So this then becomes secant squared. So this is another useful identity right here. Now I've got one more for you. Let's say that instead of dividing both sides by cosine squared, we decide we're going to divide both sides by sine squared. So if we do that, then this sine squared divided by sine squared becomes 1. And then this cosine squared divided by sine squared becomes cotangent squared, because cosine divided by sine is cotangent. Then this 1 divided by sine squared becomes cosecant squared, because 1 over sine is cosecant. So here we have a bunch of different Pythagorean identities, all in different forms. And they allow us to work well with trig expressions that have a squared in them. You can see all of these squareds. And so it allows us to substitute in situations where we've got a trig function squared. Alright, next up then, we've got some trig expressions that we're asked to simplify. We're told to simplify each into a single trig function with no fractions. Let me get this out of the way. Alright. So this first one is cosecant of alpha times the tangent of alpha, that Greek letter alpha, which is basically like our A in our alphabet. Alright, so I'd like you to remember this piece of advice. Just typing it out. When in doubt, sine and cosine it out. You might also hear me say Widsasio, an acronym for when in doubt, sine and cosine it out. So if you're not quite sure how to simplify, try to change everything into sines and cosines if you can. We'll do that in this example here. Let's get back to the inking. So I want to change this cosecant of alpha into sine or cosine if possible. Then I look up here and I see that cosecant is 1 over sine of the angle. Then this tangent of alpha, look to your reciprocal identities. You'll see that's sine of alpha over cosine of alpha. Alright, so now we've got two fractions being multiplied together. We can simplify when we have common factors in the numerator and denominator. We've got that here. Then we multiply straight across. We've got 1 over cosine of alpha. And we need to make this a single trig function with no fractions. It's got a fraction now, but I notice that 1 over cosine of an angle is secant of the angle. So this becomes secant of our alpha. And then we've got a single trig function with no fractions, so we are done. Next up, secant of t. We look at our reciprocal identities, and that is 1 over cosine of t. And tangent is the sine of t divided by the cosine of t. Now in a lot of these you're going to have to remember different strategies for simplifying expressions that you learned in algebra. One of these is if we have two fractions being divided by each other, we can keep the first one, change the main division into multiplication, this division into multiplication there, and we do the reciprocal of the denominator. It's the old keep, change, flip method. Alright, so now we are multiplying. These cosines cancel. We've got 1 over the sine of t. And the reciprocal identity for 1 over sine of t is cosecant of t. Got a single trig function, no fractions. Alright, next up, I'm going to stop the video right here. Video number 2 is going to have these last two trig expressions to simplify. So we'll pick things up in video number 2. See you then.